Financial Modeling, Topic 3, Computing Portfolio Risk and Return. Some of this information is from Financial Modeling, 3rd edition, from Simon Benenga. In this topic, we're going to talk about computing correlation and covariance matrices, computing standard deviation of a portfolio of risky assets, using matrix algebra to compute portfolio risk and return, and using VBA comments and application.object. So we'll grab this data by double-clicking and pasting into Excel. So what I have here are 10 years of returns for the S&P 500 index fund, a EFA index fund, which is developed nations, less North America, an emerging market fund. All right, so again, these are 10 years of returns, monthly returns. And I also have as an input the expected return of SPY, EFA, and EMA, which I would have used from judgment, either using, say, CAPM or Global CAPM or some other model. I have standard deviations annualized for these three assets. Again, I would use some model, either historical standard deviations or maybe an exponentially weighted moving average volatility, or GARCH, or an implied volatility from an option. And I'm looking to build a portfolio. It's 50% SPY, 40% EFA, and 10% EMA. The first thing we'll do is calculate expected return. The expected return of an n asset portfolio is the sum from I equal 1 to n. Now I is the asset. In this case, we're going to have three assets, so it's going to say from I from 1 to 3, WIRI. And the way you use this sum function is the I acts as a counter. And if we have three assets, I is going to count from 1 to 2 to 3. So we set I equal to 1. Type in WIRI. So we have W and R 1. Set I equal to 2. Compute W2 R2. And then set I equal to 3. So the way this sum function works is you set I equal 1 to the number of assets, plug in the I, 1, 2, 3, and then sum up the three numbers. Now in Excel, that's quite easy to do. We can just do a sum product. So the expected return of this three asset portfolio is just going to be 6.5% times 50% plus 675 times 40% plus 775 times 10. Or we can use Excel's sum product function. Sum product, we can go ahead and put the weights and the means, or expected returns. So we have an expected return of this portfolio of 673 basis points, or 6.73%. Now we're also going to show how to use matrix algebra to solve this problem, because it's not really needed for expected return, but when we get to calculating standard deviation, it's actually quite helpful. So when we talk about a matrix is just a rectangular array of numbers. It could be a single row, we call it a row vector. It could be a single column, or a column vector. Now in Excel, they generally use the word array. So this would be an array, also called a matrix. This would be a column vector. This would be a row vector. A single letter is often used to denote a matrix. So we say that maybe this might be matrix A. And we're going to refer to elements in the matrix using a row-column identifier. So when we talk about item Aij in matrix A, the I is the row and J is the column. So Aij is the item in the ith row and jth column. Now multiplying matrices is going to be quite useful later on when we talk about the standard deviation of a portfolio. When you multiply matrices, say matrix A times matrix B, we write the new resulting matrix A times B, or we just simply refer to it as AB. Now, when you multiply two matrices together, you can only do that if the two matrices have the same inner dimensions. In other words, you can think of matrix A having dimensions RC and matrix B having dimensions RC. Now, there are R number of rows and C number of columns. You can only multiply matrices together if the inner dimensions are the same. In other words, matrix A has the same number of columns as the rows in matrix B. And the reason that has to work is when you multiply matrices together, each item in the new matrix is really a sum product of a row in the first matrix times a column. A row in the first matrix times a column in the second matrix. So they have to have some dimensions the same in order to do a matrix multiplication. All right, so again, each element of a new matrix, say AB, when you multiply A times B, each item is going to be a sum product of the ith row of A times the jth column of B. So again, item ABIJ is a sum product of the ith row of A times the jth column of B. In Excel, we use the mmult function, where you say equals mmult, put in a matrix, comma, another matrix, or again in Excel we call them arrays. And then when you enter the formula across a new matrix or array, you take Control-Shift-Enter to enter the function. So let's do an example. Let's grab this data here. I'm going to double click on that, just in yellow. And then I'll go to Excel. And there it is. So here's matrix A. Matrix A is a 2 by 2. And a good way to kind of cheat that is look up here when you highlight your matrix. It says it's a 2 by 2, 2 rows by 2 columns. And then when I highlight B, so this is my matrix B, you can see that's 2 rows by 3 columns. Now you can multiply a 2 by 2 by a 2 by 3 because it has the same inner dimensions, 2. And then the resulting matrix, when you multiply two matrices, is the new matrix AB has the outer dimensions. So this new matrix is going to be a 2 row by 3 column. So I'll just go ahead and highlight that. Actually, I can make that a calculation. So when I multiply AB, it's going to wind up being a 2 by 3. So the way you enter a matrix operation in Excel is you highlight the entire new matrix and say equals mmult. Go ahead and put in A, comma, B. Control-Shift-Enter. So this is matrix AB. So let's talk about each item. Alright, so this item here, AB11. AB11 would be the way we identify the first row, first column of A, B. This item here is actually the ith row of A times the jth column of B. So AB11, so to be the first row of A times the first column of B. So it would be 2 times 6, which is 12, minus 6 times 5, which is 30. That'll give us 42. So again, it's like a sum product, each number. This item here, this would be A, B, second row, third column. AB 2, 3 would be the second row of A times the third column of B. So it would be minus 9 times 12 plus 3 times 4. So that would be 12 plus 108, 9 times 12. That would be 120. So again, when you multiply two matrices together, each item in the new matrix is a sum product. So we can use this idea to calculate the expected return of a portfolio. One way of calculating the portfolio or writing the expected return is W transpose R, or WTR. Now let's think about what that means. If we go back to our original problem here, let's give this a named range. Let's call this W. Now I'd like to call this R, but I'm not allowed because R and C are not allowed to be named ranges, I guess because of row and column. So I'm going to call this an RET for return. So now I have weights, W, and returns, RET. So another way of doing it, instead of doing a sum product, is what I can do is I could multiply weights times expected returns, but using mmult I can't do that because I can't take a 3 by 1, 3 rows, 1 column, times another 3 by 1. The inner dimensions aren't the same. But if I can flip this, if I can turn this into a row vector, that would then be a 1 by 3. multiplied times a 3 by 1. Inner dimensions are the same, 3. And the resulting matrix would be a 1 by 1 or a single cell. So let me show you how to do that in one formula. Equals mmult. Let me transpose W. So that's going to flip W to make it a row vector. And then I can multiply times return. And then again, I'm going to use Control, Shift, Enter. And that's another way of getting the expected return. The expected return of a portfolio is transpose WR, where W is a column vector of weights and R is a column vector of returns. Now, to calculate the standard deviation of portfolio, we can't just take the weighted average standard deviation of each element, because the portfolio standard deviation or risk is going to be much lower, or going to be lower than the weighted average if the assets aren't perfectly correlated. If the assets are perfectly correlated, it does turn out to be the weighted average, but that's rarely the case. The way we write the variance of an n-asset portfolio is the double sum I equal 1 to n, j equal 1 to n, wi, wj, sigma ij. So again, these are our counters, just like we used in expected return, except there's two of them, I and j. W's are the weights, say the weight in asset I times the weight in asset j. And sigma ij, that's how we denote a covariance term. So sigma ij would be the covariance between I and j. One way of thinking about a covariance is the correlation between two assets, at I and j, times the standard deviation of each asset. So let me show you how to use this double sum to calculate the variance of an n-asset portfolio. So again, it's the double sum, I equal 1 to n, j equal 1 to n, wi, wj. So now we have three assets. So n is the number of assets, so we're going to say I equal 1 to n and j equal 1 to n. So to do that, we set I equal to 1, then we set j equal to 1, 2, and then 3. Once j has reached the maximum, there are three assets, we set I equal to 2 and j equal to 1, 2, 3. And then we set I equal to 3 and j equal to 1, 2, 3. So one way of thinking about that double sum, it's a trick, kind of a mathematical trick to ensure that you figure out all the pairwise combinations with assets. So if there's three assets, there are three pairwise combinations, 1 with 1, 1 with 2, 1 with 3, 2 with 1, 2 with 2, 2 with 3, 3 with 1, 3 with 2, 3 with 3. And the reason why we have to do that is the variance of an n-asset portfolio depends on two things. One, all the variances of each asset, so how risky the individual assets are. We're going to measure that with standard deviation. And it's also going to be how all the assets interact with each other. In other words, how are they, when you put them together, how much of a diversification effect do they create? And those are all the covariance terms. So when we do this, we set I equal to 1, j equal to 1 again, and then we plug in wi, wj, sigma ij. That's w1, sigma 1, 1. Now it just so happens that would be w1 squared, the weight in the first asset squared. And then the second term, sigma 1 squared, or I'm sorry, sigma 1, 1, the covariance between 1 and 1. I'm going to show you that that actually turns out to be the variance of asset 1. And then you plug and chug I equal 2, j equal I equal 1, j equal 2, w1, w2, sigma 1, 2, and then w1, w3, sigma 1, 3, and so on. So the variance of an n-asset portfolio is the sum of these 9 terms. All right, 9. We'd add up these 9 numbers, and then we'd take the square root of that, and that would be a standard deviation. Let's talk about what covariance and correlation mean for a minute. All right, so the formula for variance is the average squared deviation from the mean. So I'd take an asset minus return in one period minus its mean return, and then I'd add up the squared deviations for all the assets and divide by number of observations, or not all the periods, and divide by number of observations. So again, variance is the average squared deviation from the mean. Covariance is the average of the product of deviation for the mean of two assets. So in other words, stock 1, is it above, might be above its mean in period 1, subtract its mean, and then asset 2 might be also above its mean in period 1. So I'd take the deviation for asset 1 in period 1 times the deviation of asset 2 in period 1, and I'd do that for all the observations. So let's actually go here and take a look at this little exercise I put together. Again, we're not going to use this, but just it's a good idea of figuring out or thinking about how standard deviations, variances, covariances and correlations are calculated. So I just made up some data here. So say you had stock A and stock B, and these are their 5 monthly returns. The average of stock A is 12% return. The average of stock B is 16% return. And then I have one more column. This is the deviation in period 1 for stock A. So stock A at 10% return minus the mean of 12%. Oops, I got to move that. Minus the mean of 12%. So that's a minus 2% deviation. So these are the deviations from the mean for each asset. And then the second one, we'll take the return of stock A or B minus the mean. Oh, I forgot to anchor the last one. Let's go ahead and anchor this. And let me anchor this one too. Gotta anchor both of them. Alright, so now I have the deviations of stock A, the deviations of stock B. I can then take these squared deviations in each period, and if I averaged up the squared deviations for stock A, that would be the variance of A. If I added up or if I took the average of the squared deviations for stock B, that would be the variance of B. Or I can use Excel's function var P, which is the variance, population variance. If I then take the square root of variance, I'd have the standard deviations. So again, this is just if you have returns and a mean, take the deviations, square the deviations, take the average square deviation, and then you have variance. Take the square root, you have standard deviation. Now, if I talk about the covariance between asset A and asset B, I would take the deviation in stock A in period 1 times the deviation of stock B in period 2, minus 2 minus times 4. That would be the product of the deviations. I would then copy that down. So now these are my 5 products of deviations. Take the average of that, and that is covariance. So covariance is a measure of how the assets covary. Specifically, it's the average product deviation. So let's think about what the number means. So the number is positive. What that tells you is these assets tend to move together. They both tend to be above and below their mean at the same time. So let's look at period 4. Stock A had a really bad period. Stock B had a really, really bad period. So in that period, stock A was 22% below its mean, and stock B was 36% below its mean. So I take the product of deviations, minus 22 times minus 36, I guess minus 7.9%. So notice negative times negative, you get a positive deviation product. So when assets tend to move both negative, you get a positive number. If they're both well above their mean in period 3, they get a positive number. Now when they move in different directions, they get a negative number. So when you see the covariance is positive, what it's telling you is they tend to be both above their mean or below their mean at the same time. Now this number of covariance, 2.7%, it's hard to interpret. I don't know, okay, they tend to move together, but is that a strong measurement? Well, we use one other measure to talk about how strong the relationship is, and that measurement is correlation. Correlation is the covariance between the two assets divided by the product of the two deviations, and that number is bounded by 1 and negative 1. So when we calculate the covariance of asset 1 and asset 2, divided by the product of the two standard deviations, you get 0.98. And what you see is that's a very strong relationship. 1 would be perfectly correlated, negative 1 would be perfectly uncorrelated, or negatively correlated. So that's what variance and covariance and correlation mean. That's also why I said that the covariance between asset 1 and asset 1 is the variance of asset 1, because all you would do is take the deviation of stock 1 period 1 times the deviation again, which then would be the product of the the deviation squared, which by definition is the variance. So to calculate an n-asset portfolio variance, we need to know the variance of each asset, and this little trick gets us the 3 variance terms. sigma 1 squared, sigma 2 squared, sigma 3 squared. And we need to know how all the assets interact, which are these terms here and these terms here. When we talk about covariances, we like to write them in this way. We'll take a matrix or an array of all the covariance terms. So here is covariance between 1 and 1, which actually is the variance of 1, 1, 2, 1, 3, 2 with 1, 2 with 2, 2 with 3, 3 with 1, 3 with 2, 3 with 3. So this is a visual array or matrix of all the covariance terms. Sometimes this is also called the variance-covariance matrix, because these terms are actually variance terms. This is the variance of 1, variance 2, variance with 3. This off diagonals, or these off diagonals, are actually all the covariance terms. Also notice that sometimes we don't even need to show both off diagonal sets, because the covariance between 2 and 1 is the same with 1 with 2. 3 with 1 is the same as 1 with 3, and 3 with 2 is the same as 2 with 3. Now, if we know all the covariance terms, if you don't want to write the calculations for variance this way, which gets really bad, especially if you have, say, 10 assets and you have 100 rows, there's 100 pairwise combinations of 10 with 10 assets. You could just array the numbers or display the numbers this way, and then if I multiply each one of these covariance terms by the weights, I will get the same result. So another way of writing portfolio variance is this way. You can see the covariance terms, and I'll just multiply each one times the weights. So let's do this in Excel. Let's first create a correlation matrix using Excel's correlation data analysis function. We'll then use that to calculate a covariance matrix. So back to our original sheet. I'm going to go ahead and hit Data, Data Analysis. Make sure you have the add-in of Data Analysis. I'm going to ask for correlations. I'm going to put the data in under the input range of all the returns for these assets. I'm going to click on Labels, since I also included the names of the stocks or the assets. And then as output, I'm just going to put it right here, and it'll paste it right here for me. So I hit OK. Again, these are the asset returns including the label. I clicked on Label, and in the output range, I put it right here. Okay, so there's my correlation matrix. I'm actually going to highlight these and make them a cell style of input, since these are values. So notice the correlation matrix also is a visual array, or just an array of correlation terms, and it only shows half of the matrix, all right, because these numbers are repeated. So I'm just going to put calculations here. IFA and SPY is the same as SPY and IFA. That's the same, and that's the same, and I'll make these a calculation. And the reason why I'm doing these cell styles is if later I wanted to go back and make some changes, assumptions, and correlations, I know that these are values. These are not linked to the data. If the data were to change, these would not change. So now I have a correlation matrix. Now I said that we're going to need covariance terms to calculate portfolio variance, and I also said that the covariance of an asset is the correlation times the two standard deviations. So here's correlation equals covariance divided by the two standard deviations, or the covariance is equal to the correlation times the two standard deviations. So we could do that. So we're going to convert a correlation matrix into a covariance matrix. How I do that is take, say, each number. So this would be the covariance between SPY and IFA would be equal to the correlation of SPY and IFA times the standard deviation of SPY times the standard deviation of IFA. And then I'd have to repeat all these calculations and then fill in this off diagonal. So that's the hard way to do it. It would be to put in my cell formula, especially again if we're doing 10 assets. It would be 10 by 10 matrix, 100 values. Let me show you a little trick. Instead of doing it this way, one at a time, I can highlight this whole area. In fact, first of all, let's do another named range. Let's call this, without the labels, let's call that core for correlation matrix. Alright, so I gave that a name range of core. Let's call these three standard deviations vols. So now I have core, I have vols. So it's now, write this function, this calculation, equals vols times transpose vols. Again, that's just looking at this range here, times core, which is this range here. And I highlighted this entire thing with the formula. Notice how all of it's highlighted. Now to hit any formula, or to enter any formula across an array in Excel, you have to do Control-Shift-Enter. So there's that number popped back up. All right, now if you multiply arrays in Excel without using mmult, what it's doing is it's not doing matrix out, it's not doing matrix multiplication. It is simply lining up the values and multiplying together. So let's think about what that means. If I were to do an mmult, it would be, say, an entire row of A times an entire column of B. But when I just simply do this times the transpose of this times this, it simply lines it up. So this number here is going to be this times a transpose of this, turning it into a row vector, times this. So effectively what it does, it's just going to line up and take this value, none of the other values inside this spreadsheet, this one, times this value, again, times no other values in this vector. And then once it transposes it, it's going to pick up SPY. Okay, so this is a little trick to create a covariance matrix from a correlation matrix. Now here, if you double click here, there's a little discussion of what it means to do an mmult versus entering, say, A times B and just hitting Control-Shift-Enter. So if I did mmult A times B, so A is a 1 by 3, B is a 3 by 3, it creates a 1 by 3. If I were to do an mmult, the first item here would be this row times this column of some product, which is 47. If I were to just type in A times B, Control-Shift-Enter, it would simply be 1 times 3. So it kind of lines up the row and column identifiers and multiplies the values. Now I'm going to calculate the variance of a portfolio. Now the variance of a portfolio, let's go back to this graphic. The variance of a portfolio would be each covariance term times the weights twice, such as the weights line up with the covariance. So for example, this term here would be W2, W1, sigma 2, 1. So we're going to calculate the total variance by adding up 9 numbers. We're just going to line them up here. So for example, we're doing this variance calculation. I need to take a covariance between the two assets, again, times the two weights. This is SPY and EFA. So I take the weight of SPY times the weight of EFA. So now I have this number times these two numbers. And then I could repeat and do, say, SPY and EMA and just do the rest, add up these 9 numbers and calculate the variance. But again, there's going to be a trick just like the last one. Let's give this matrix right here a name. Let's call it CovMat for covariance matrix. Again, and we already called this column W. So I can just highlight this whole range, equals W times transpose W times CovMat, Control-Shift-Enter. these are my 9 terms. If I add these numbers together, let's go here, just say sum. I add these numbers together, that'll give you my portfolio variance. If I then took the square root of this number, that would be the portfolio standard deviation. That is the portfolio standard deviation of a portfolio that's 50, 40, 10 invested in SPY, EFA, and EMA is 16.39. Let me point out one thing before we return. That is, these are vectors of monthly returns. We use those to calculate a correlation matrix. And then I combine that with annualized standard deviations to create a covariance matrix. One thing I have to point out is this is now what we call an annualized covariance matrix, because when you combine correlations with standard deviations, whatever the term of the standard deviation is, that's the term of the covariance matrix. In other words, if these are monthly standard deviations, this would be a monthly covariance matrix. If these were weekly standard deviations, this would be a weekly covariance matrix. And that's because correlations have no time specification. It's just a measure of relationship. It's not over time. It just tells how the assets move. So what I say is the correlation between SPY and EFA, the daily correlation is 0.89, the weekly correlation is 0.89, the annual correlation is 0.9. So when we take a correlation matrix and combine it with a standard volatility matrix or vector, that creates a covariance matrix with the same period as the original, which allows you to calculate variance terms. So that's why this is the annualized standard deviation. And the last thing we're going to do, or one of the last things we're going to do, is show you how you can use matrix algebra to calculate portfolio variance. So we said that the variance of an net asset portfolio is the double sum Wi, Wj, sigma ij. So another way of writing that in matrix algebra is the variance of a portfolio's returns is the transpose of W, SW. So again, all you have to do to calculate variance of the portfolio is we need to get 2 weights times each covariance term to create this matrix here. Right, that's our final matrix. We summed all the numbers together. So if we can get some kind of mathematical trick to multiply the weights twice, making sure they increment the right way, and get a covariance term for each one of them, we can calculate it maybe in one step. Now the reason why it is W transpose SW is we need a row vector weights, a 1 by n matrix, 1 row, n columns, times an n by n matrix. Covariance matrix is always square, so we say it's size n by n, say 3 by 3 if there are 3 assets. The inner dimensions of when I multiply these two together is an n by n. It then creates a 1 by n, 1 row, n columns, so it creates another row vector. And then I take that resulting matrix multiplication and multiply times weights again. I'm now taking a 1 by n, which is the result of this, times a n by 1. That creates a 1 by 1, which will calculate our variance in one step. So the variance of an n asset portfolio is W transpose SW, where S is the covariance matrix. We write that in Excel by saying M mult transpose WSW to the 1/2. So in other words, I have to do this M mult, take that result, multiply again using another M mult, and take the square root. So we can write that. We can say equals M mult. Well, actually, let me do a named range first. Let's call this covariance matrix S. I'm sorry. It's already called CoVarMat, so I guess we'll just use that. So we'd say equals M mult transpose W, that's my weights, CoVarMat W again. And that's another way of calculating the portfolio standard deviation. Simply calculate a covariance matrix and do M mult transpose W covariance matrix W to the 1/2 power. And now we didn't really need to do this last step, and you shouldn't have to for the rest of the lessons or lectures. If we can just get a covariance matrix, we can then calculate portfolio standard deviation. So that's the result. The portfolio has a mean of 673, the standard deviation is 639. Again, I created a covariance matrix by using historical correlations. I combine them with my estimates of standard deviation, which maybe are from implied volatilities, and I use that to compute a covariance matrix. The resulting covariance matrix has the same term as the volatilities, annualized in this case. One note, if I had a risky asset, say stock A, and I combine that with a risk-free asset, say a treasury, the portfolio mean is still simply the weighted average, weight of the risky asset times the return of the risky asset plus weight of the risk-free times the return of the risk-free. But the portfolio standard deviation becomes much easier than what we just calculated here. It's simply the weight of the risky asset times the standard deviation of risky asset. So if you know you're combining one risky asset with a risk-free asset, I don't have to create covariance matrices and correlation matrices and use M mults. I know it's just the weight of the risky times the standard deviation of the risky. And also, if you wanted to write a function to calculate, say, the expected return using matrix algebra, I'm going to call that function port mean. I'm going to have that function have two parameters. Those parameters are W, which is a range of weights, and R as a range of returns. So let me grab this function. Again, the portfolio's port mean has W as a range. Notice as range is a VBA command that says that W is not just a single cell. W is going to be an array. R also is going to be an array. So when you say as range, if you want to specify that a parameter is going to be in a range. And then I'm going to use the calculation of the portfolio mean as the transpose of W times the column vector of returns. Except when you use Excel's functions in VBA, you generally have to say application dot. So if I wanted to use, say, the standard std EVP in VBA, I'd have to say application.std EVP. Now this doesn't hold for all. For example, like the natural log function does not need, or actually does not work if you do application dot. But for most of Excel's functions, you have to use application dot. So it's application dot mmult instead of just mmult. And then I can't use just transpose W. I have to do application dot transpose. I put in W. And then that's how we can use VBA to calculate expected return. So I can take this function. Also notice I've used single quotes here to add comments. Whenever you have a single quote in VBA, it ignores everything to the right. So I'm going to copy this function, Control C. I'm going to hit Alt F11 or hit Developer Visual Basic, Insert Module, Paste. There's my function port mean. I can then calculate the portfolio mean down here by inserting a user-defined function, portfolio mean. Here's my weights. These are my returns. Control-Shift-Enter, and you have another way of calculating portfolio mean. Now I could create a function if I wanted to calculate portfolio standard deviation. I would have two parameters, W and covmat or covmat, and I would just have a calculation that the portfolio vol, whatever you want to call it, inside my VBA. So I'd have a program that looks like this, except it's going to be called, say, port vol. I'd have W as range, and I'd have covmat as range. And then I'd have a form for portfolio, or a line that says that the portvol is equal to application.mmult, application.mmult, application.transpose, W returns, and so on. So that would be a way to use VBA to calculate your values. So in this topic, we computed the standard deviation of a portfolio of risky assets, computed correlation and covariance matrices, used matrix algebra to calculate portfolio return and risk, and used VBA application.object and showed you how to use comments to calculate portfolio mean and standard deviation. Also, just to highlight, if you want to calculate the expected return and standard deviation of a portfolio, say of 3 assets, you need expected returns. A likely source of that might be historical returns, CAPM, global CAPM, a Fama French 3-factor model, or just your best guess. You need a vector of volatilities. So you might use historical, you might use, say, an exponentially weighted moving average volatility or an implied volatility or GARCH or some other model calculate volatilities. And you'll need a correlation matrix. You'll combine those to create a covariance matrix, put in your portfolio weights, and then you have your portfolio mean and volatility. So therefore you see it takes a lot of judgment to calculate just the expected return and standard deviation of portfolio, judgments in selecting these volatilities and means, and a time period for estimating correlations.